Hello. In today's video, we're going to cover the fitting methods in AstroPhot. So AstroPhot is really made around building models of an astronomical image. But then, of course, once you've got that model and all of its parameters set up, you're going to want to optimize those parameters. Depending on your use case, there's a bunch of different algorithms that might be more appropriate. And so AstroPhot includes a bunch of these already wrapped up and ready to go. And we'll discuss a little bit about extending beyond that once we've seen the main ones. So first, as always, we've got to import AstroPhot. Here we go. All right, AstroPhot is imported, and here I have a setup which is mostly just going to create some fake data for us. So it's two galaxies with a bit of noise in the image. And the point of this is just to create some data where we know what the ground truth values are. So this is two Sursic models that are relatively close to each other. And since we know that what the true values are, we can see how well the different fitting algorithms are doing. The first one is Levenberg-Marquardt. We've already seen this in the other tutorials. Levenberg-Marquardt is the algorithm of choice for optimizing most models in AstroPhot and really for most astronomical image fitting codes out there. So here we go. We can run the Levenberg-Marquardt fitter and see how it does in this problem. You can see that we started off initially with some pretty bad fitting values, and it has to work a long way to get down to a good chi-squared per degree of freedom. Now, since we created this data, we know what the uncertainty is on the data points. We should expect to get a chi-squared per degree of freedom pretty close to 1, and that's what we do here. For the Levenberg-Marquardt fitter as well, you have the extra information of this L variable, which should be very close to 0, and that would mean that you are actually at a local minimum, which in this case we hope is the global minimum. And so that lets us know that we've actually converged successfully in this case. All right, now we can actually plot these to see what they look like. And in this plot I've set up, before we started optimizing the model, this is what our initial parameters were. You can imagine this coming from some simple heuristics that get you going, and then some really actually some quite bad heuristics to get it going, because this is the residuals before optimization. They're pretty big. There's a lot of 5 sigma residuals, so it has a long way to go to get to the optimal point. Now, after that optimization that we just saw, the fit looks exactly like it should, and the residuals look like clean white noise. This is the ideal scenario that we're looking for. Really, the residual image should look like it was just salt and pepper noise drawn from a Gaussian. That's what we're looking for under the ideal scenario. Because the Levenberg-Marquardt fitter gives us a full covariance matrix for all the parameters, we can plot a corner plot that comes from taking that covariance matrix and converting it into ellipses in a big triangle. So there we go. Now here we've got the true values plotted with these lines in pink, and then the uncertainty contours are given with the blue ellipses. And you can see that there's definitely some strong correlation between some of our parameters. It looks like the brightness at the effective radius and the effective radius. Perhaps not too surprising that there's a strong correlation between those. And this is such a big corner plot because it's actually 14 parameters that we're fitting here. There's 7 parameters from one Sursic, 7 parameters from the other Sursic. And these corner plots can get pretty big. The square here, this big square, that's actually the intersection of the two different Sursic models. And you can see, especially in relationship with the brightness of one of the Sursic models, that oh no, that's the sky level. Okay, so it's 15 parameters. That's the sky level. And that sky level is correlated with a bunch of the parameters in the Sursics, which is not too surprising. The statistics themselves have some really weak correlation between each other. That correlation would get stronger the closer we put the two statistics on top of each other. All right, so that's our big corner plot with Levenberg-Marquardt. Now, I mentioned this in the group models tutorial, but there is an iterative fitter, which will basically just go one model at a time. You see sky, Sursic 0, Sursic 1, and it'll just keep looping in those until it reaches the chi-squared minimum. And this is mostly just determined by it making it through a loop a couple times and not seeing any improvement in the chi-squared. So it's not as nice as the pure Levenberg-Marquardt one, which gives us that L parameter to know that we're at the minimum. But if you run the iterative fitter long enough, it really should converge to the minimum, and in this case, it did. Just like with the Levenberg-Marquardt one, it started way off from the um, optimal point, and it made its way down to that optimal point. Now, it's not always possible, or reasonable, I should say, to iterate through one model at a time. Um, so the reason for that might be that, say, two models are sharing a parameter. And so if you tried to just fit one of them, it would yank that parameter way off in the wrong direction, and then you'd switch to the other one, and that would yank it back. And so you would just get a really bad fit. There's sort of two ways to deal with that. One is to create a subgroup model. So you take those two models and link up, say, their centers. You want their centers to line up. You put those two models into a group model, and then that group model you put into the larger group model that's going to be you're eventually going to run the iterative fitter on. So when it goes through its list of models, it gets that um, two model, that group model, it gets to that one and fits both of them simultaneously using Levenberg-Marquardt. It's perfectly okay to nest group models in AstroPhot. That's allowed. And so that's one way to deal with this problem. But if you have a parameter that's shared among a lot of models, say a PSF that is shared across all of your models, and you're trying to optimize that PSF along with everything else, then it doesn't make sense to go one model at a time because each one is going to yank that PSF in a totally different direction. That's where iterative fit param comes in. So if you've got this huge model that's way too big to fit into Levenberg-Marquardt, and it's way too distributed with its constraints to fit naturally into the iterative fitter, then that's when you use the iter param model. And this one, instead of going one model at a time, it goes through chunks of parameters at a time. So in this case, we've got 15 parameters. And so we do chunks of size 5. It'll pick 5 random parameters, in this case, random. It'll optimize those 5 parameters, and then it'll switch to a different set of 5 parameters and optimize those 5 parameters. And then it'll switch to a different set of 5 parameters and optimize those. And it'll keep looping in this way until it finds the minimum. This one actually runs a little faster than the other iterative algorithm. And um, that's because sometimes it's more natural for the fitter to move through chunks of parameters at a time. And so in this case, it worked pretty well. And if we plot that, there we go. Just like before, we're getting those nice clean residuals. So it definitely found our chi-squared minimum in that case. And that was without ever examining or creating the Hessian for all of those parameters at once. The nice thing about iter_param as well is that it will give us a covariance matrix. Keep in mind, though, that it's only going to get the covariance between parameters that were in the same chunk. So within a chunk of 5 parameters, it'll get all the covariances between those, but it won't get the covariance between chunks. Maybe a future update will include computing those covariances just to make things nicer, but for now, it doesn't include those. And here we go, we get a nice corner plot just like before. Okay, so those are the Levenberg-Marquardt based fitters that are just ready to go in AstroPhot. There's other cases where you might not necessarily want to use one of these Levenberg-Marquardt based fitters. So SciPy minimize is a universally used package in Python for minimizing functions, or in our case, maximizing a likelihood. So you just got to put a negative on there. And since AstroPhot has a functional way to interact with it, like I talk about in the overview here, model dot Gaussian log likelihood is a function of x that returns the Gaussian log likelihood. And so you can pass that function into SciPy minimize. You can do it yourself, or you can use the wrapper that I've already created within AstroPhot to do this. Keep in mind that x, that vector, you can get that at any time just by calling model.getValues. You call model.getValues, it will create a 1D vector, and that vector can go into Gaussian log likelihood and be used by something like SciPy minimize. So let's give it a try. Unfortunately, um, the SciPy minimize fitter doesn't have access to that second order information that Levenberg-Marquardt has access to. And so it can take a really long time to fit. The standard algorithm to use is LBFGSB, which is actually quite similar to Levenberg-Marquardt in its conceptual framework, but it only uses gradient information and it tries to guess at the second order information. It doesn't just have access to it. And so it takes a lot longer to fit. I've restricted it in this case to 500 iterations, so it won't find the minimum, but it should get decently close. You can use any of the SciPy minimizers, and as I mentioned, because you can access an AstroPhot model, you can access the likelihood for an AstroPhot model in a functional way, you could really truly use any minimizer that you like. You could write your own gradient descent algorithm. That's totally fine. So any of those should work. I've just written this wrapper for you to make it easier. Some of these fitters take a little while to run. This one's taking over a minute. I think it takes about a minute and a half. So we'll just let it go. And I should mention as well that all of the SciPy fitters have a criteria for success in them, so they can tell when their optimizer should stop running. Unfortunately, those success criteria are not always sufficient for um, astronomical image fitting. So I've noticed with some of the algorithms, when they reach their success message and you plot the residuals, you can still see structure in the residuals. That's, I guess, because optimizing uh, a very complicated astronomical image likelihood involves perhaps some valleys um, in the surface of their likelihood, and perhaps convinces the fitter that it's found the minimum when in fact it's just moving along a shallow valley. In this case, if we run, we see that it's done a decent job. It's come a long way towards that maximum likelihood, but it has not quite reached it yet. There's still some clear structure in the residuals. This is not the nice white noise that we're looking for. But um, sometimes when you have a really, really big model, and where the iterative fitters aren't an appropriate fit for your case, then the gradient descent is the only way to go. And you just have to let it run for a really long time until you converge to the minimum. For fun, I also created my own gradient descent code. It's called Slalom. It's very simple. All it does is find the gradient, take a couple of points along the gradient, fit a parabola, and jump to the minimum of the parabola. That's the whole thing. And so this one, it runs through its steps pretty quickly. It is obviously gonna take longer than the Levenberg-Marquardt because it's purely based off of the gradient information. There is a momentum parameter that you can include in there. The momentum helps it keep going faster when it is going in the right direction. But if it encounters a situation where the momentum is pushing it off course, it just kills the momentum and starts over. And just like that, it has finished running. And you'll see that the residuals, similar to SciPy minimize with its gradient descent, have not quite converged, but they're definitely on the right track, certainly compared to the residuals before optimization. And so for something like this, you just need to run it a lot longer to really make sure that you're at that minimum. Now, so far, we've only talked about optimization, seeking as fast as we can the maximum likelihood point. But we're not always only interested in the maximum likelihood point. Sometimes we want to explore the likelihood surface, or if you look into some of the later videos, we might be doing a Bayesian analysis and we've got a full posterior distribution that we're trying to explore. So the metropolis adjusted Langevin algorithm is a type of Markov chain Monte Carlo sampling algorithm. It uses a metropolis Hastings accept reject step, although it takes advantage of gradient information to propose more efficient steps in the parameter space. So it's going to randomly surf around um, the likelihood set base and either accept or reject those steps based off of the Metropolis Hastings. And in the end, it should sample in a distribution that is roughly equal to our likelihood distribution. You'll notice that there are certain controls you have, the number of iterations, the number of chains. Epsilon is just basically connected to the step size. The mass matrix is incredibly important for getting efficient sampling. I've cheated just a little bit here. I used Levenberg-Marquardt to get to the optimum point, to the maximum likelihood, and then I took the covariance matrix from that optimum point, which is essentially the Fisher information matrix, and I used that as the mass matrix. As a little bonus, I changed the likelihood over to using a Poisson likelihood instead of a Gaussian likelihood. There are certain cases where you'd want to use a Poisson log likelihood rather than a Gaussian log likelihood. A lot of the fitters, almost all of the fitters in AstroPhot, can let you switch between a Gaussian likelihood or a Poisson likelihood, just depending on what case makes the most sense for you. For most cases, Gaussian, and that's the default that AstroPhot assumes. Okay, now now that we've got a sampling algorithm, instead of plotting a bunch of ellipses, we can actually do a corner plot where we do 2D histograms of all the data points that we've collected. So this was 4 chains times 300 points, so 1,200 data points that we've got in our corner plots here. And you can see how they fill out very similar contours to what we had with the Levenberg-Marquardt fitter. But there are some differences, mostly in the tails. The tails tend to be more extended in these samplers because they're truly representing the likelihood distribution and not just a Gaussian approximation from the maximum likelihood. So in these contours, you can see some little fuzz coming off on the edges, and that actually extends out decently far compared to what our uh, expectation would be with the Gaussian approximation that comes from the Levenberg-Marquardt fit. So there are cases where you care about these heavy tails and you want to actually understand them. The best way to do that is with a sampler. There's other kinds of samplers. So AstroPhot includes a wrapper for the Pyro HMC uh, sampler. Hamiltonian Monte Carlo is very similar to Mala, except where Mala always takes one step. HMC will use the gradient information to take a large number of steps and sort of like follow along the trajectory of uh, a potential. It really treats the likelihood as if it's a potential well, and you've got some particle flying around in there, almost like it's in gravity, and it'll traverse for a little while, and then it'll stop, and that's your new sample that you're going to try and use the accept reject stage on. I don't, yeah, anyway. So this one takes a little longer to warm up and then run. It's trying to use Pyro, so uh, Pyro has its own procedure for initializing the chains. Once you get things the way you like them, you can let it run for a long time. A lot of warm-up steps, a lot of iterations, and it'll get you really, really good results. I personally find Mala to be easier to tinker with, but uh, Hamiltonian Monte Carlo with Pyro is kind of nice because it's a bit more of a set it and forget it kind of algorithm. Uh, Similarly, I cheated a bit and just forced the mass matrix to come from the Levenberg-Marquardt Gaussian approximation at the maximum likelihood. So that just makes the sampling a little more efficient and lets us skip a bit of the warm-up. I just set warm-up to one step because I know I don't need it. I've already set some decent values after tinkering around for a while. This is for demonstration purposes. And so in reality, you'll have to run things for quite a bit longer in order to confidently converge and to get decent sampling all the way through your likelihood distribution. But this is a tutorial, so I get to cheat a little bit, and I know that I've already set a lot of these parameters to decent values. I wanted the whole thing to run in under 2 minutes, so it didn't actually take very many steps. Each step takes a lot longer to do in Hamiltonian Monte Carlo because it has to essentially do 10 gradient evaluations in order to follow along that. It gets 1/10 as many samples as Mala does for the same amount of time. The hope is that those samples are more efficient in the end. And so if you run it for longer, you'll get very well filled out posteriors. But for the sake of the tutorial, I just took fewer samples and I've blurred the data a bit so it looks nice and smooth. And you can see that we're getting contours that are pretty comparable to what we had with Levenberg-Marquardt or with Mala. It's fitting decently well. Finally, if you're really stuck and your algorithm, for some reason, you can't calculate the gradients. It happens sometimes. Perhaps you've made a custom model and you did something which broke the gradient calculation. It's totally fine to make custom models in AstroPhot, but if something along that line breaks the gradient calculations, um, then you're not going to be able to use any of these gradient-based samplers. So AstroPhot includes a wrapper for the emcee package, really widely used, fully density-based sampler. So that one, all you need to do is calculate the likelihood in order to run it. And so that one's much more stable in terms of gradient calculations, doesn't need those. So once again, to cheat a little bit, I use Levenberg-Marquardt just to get us to the maximum likelihood point, and then I start our sampling. I only let it do 200 samples, but it is going to do a lot of chains simultaneously. It's got a whole bunch of chains going. So it's actually got quite a few samples by the end. It's just that those chains haven't had as much time to explore as they really should. So you'll see that the corner plot doesn't come out quite right. But that's okay. If you run it for longer, you will get a good result. emcee is a very powerful algorithm. It'll work in the end. It's just going to take its time to get there. And that's partly because it just doesn't have access to that gradient information. Okay, so here we go. It's finished fitting. Um, and now we're going to let it generate that corner plot for us. Here we go. It takes a little while to make the corner plot. This is really more of a matplotlib thing. There we go. So you can see all of the chains started at the maximum likelihood point, and so they're all pretty close to the true value, and they've just been sort of exploring out, and they haven't quite got far enough yet to really represent the likelihood distribution yet. They would eventually get there. That's guaranteed. It's just I don't want to let it run for too long because then it's going to take forever. Okay. Um, so now that we've run through all of these fitters that are available for you in AstroPhot, let's just do a quick show of how you go about making your own fitter work with AstroPhot. So initialize model. Let's say, for the sake of argument, that you've already loaded in your data into a target image. You've created your model, which in this case is a group model, Sky, Sursic, Sursic. And you've got some decent starting parameters. You ran initialize and AstroPhot figured out those for you, or you already knew them from some other analysis. So we're ready to go. We're teed up. We want to start doing some fitting. How do you go about that if you're not going to use one of the fitters that's already here? Well, to start off, you need your initial point. And to do that, model.get values. So this will return a 1D tensor. So let's try printing shape. There we go. So this is a vector of length 15. It's those 15 parameters that we had in our that we have in our full group model, which is those three models combined. So that's that vector. And then if we do model dot Gaussian log likelihood, and let's send in x naught. Let's print that. There we go. This is our Gaussian log likelihood. So this is negative 0.5 times the residuals squared, the sum of the residuals squared. Now the residuals in this case, I'm talking about the difference between the model and the data divided by the variance. So that's what this number represents here. And so you could very easily imagine setting something like SciPy minimize for the function. You give it model dot Gaussian log likelihood. You give it x naught, and you select some method. So because AstroPhot in this case is working with PyTorch, or if you switch it over, it could work in JAX. Either way, SciPy minimize is assuming NumPy arrays. We can get around that with a simple lambda function. So in this case, all we have to do is torch tensor x and then item. So what this is going to do, this is going to take, you see, we take our x naught, our initial parameters, and we detach those into a NumPy array. So that's all set to go. SciPy minimize is going to pass in some vector x, which is going to be the current set of parameters it wants to test out. We convert those parameters into a torch tensor, and so now PyTorch is perfectly happy to run this Gaussian log likelihood. And then once it returns the likelihood is just a single number, just like this. So we can call dot item on that, and item just basically returns a single number. If you're going to do a vectorized version, then you'll need to do detach CPU numpy in order to get that full vector of different likelihoods out. That would be relevant if you were running an MCMC algorithm with multiple chains. You can vectorize it and then detach that at the end. So this is pretty much all you would need to run SciPy minimize with Nelder-Mead on an AstroPhot Gaussian log likelihood. This would be ready to go. It would probably run for a really long time because it's a 15-dimensional parameter space that's very spiky. So it's very challenging to optimize. But SciPy minimize is pretty powerful. It would get there in the end. So that would totally work. And if you were going to run some sort of MCMC sampling algorithm, the setup would be very similar. You just need to call your log likelihood function. Oh, you'd probably want to negative it because you do want to maximize your likelihood, not minimize your likelihood. So make sure to put that negative in there. If you want to do a Poisson log likelihood instead, Poisson log likelihood. Okay, that's all that would take. Now let's say we want to go one step further. We have some creative idea for a prior that we want to do on our model, or we have some constraints that we want to loosely enforce, or we have a different idea of what the likelihood should look like. Maybe we don't want to do the sum of the squared residuals. We want to do the sum of the squared residuals, but clip anything that's too large. That's something that can be done in certain contexts. So how would we go about that? Making our own likelihood function? Well, it turns out that the likelihood functions in AstroPhot are actually pretty abstracted and quite simple already. So if you wanted to make your own, let's um, let's just clear this out. So let's my likelihood, and it's going to be a function of x because that's all we need to do. Let's first just recreate the basic Gaussian log likelihood. Okay, so log likelihood negative 0.5 times. Now look at that. Um, it seems that my code already knows what to do here because it's seen it a few times, but this is pretty much it. So model target data minus model, given that x parameters that we've just passed it, it's going to create a model image based off of those parameters for the model. We just grab that data, and now This is our residuals squared. That's the variance, and we're ready to go. The actual way that AstroPhot goes about this is a little more robust. And so just to show you what you really should do under best practices, you would do flatten data and flatten data. So if you're fitting just a single image, this doesn't matter. But if you're fitting multiple images, then re requesting data is going to return for you a tuple of PyTorch arrays rather than just a single PyTorch array because the different images could have totally different shapes. And so AstroPhot doesn't know that it can combine them like that. So by calling flatten, what you're doing is you're telling AstroPhot to take all of those images, flatten them out into absolutely gigantic 1D vectors, and then just concatenate them all together. So if you've got a lot of images and you're combining them all together, this will create just an absolutely massive vector of all the pixels all in one direction. It gets pretty big, but that's okay. Um, so it'll do that. Similarly for the variance, you do flatten variance. So now we've got that. And keep in mind that some pixels we maybe don't want to analyze. We've masked them. So the simplest thing to do is to just do, let's see, we're going to multiply that in. Model dot target dot flatten mask. And now the mask is 1 for masked and 0 for not masked, which is pretty standard for masks. So we just do the negative of that. So now it's going to be 1 for pixels that we want to keep and 0 for pixels that we don't want to keep, which of course means that we can multiply it by our data. And so it'll multiply by 0 all the data that we don't care about. And this will create the likelihood that's right in AstroPhot by default. This will recreate that exactly, but you can now go and modify it however you like. You've got the key pieces that you need, the data, the model, the variance, the mask, and they're all abstracted away for you so that you can just treat them as these separate things and go ahead and build your likelihood function however you like. Or if you wanted to add some prior, say model dot, um, let's see, models, and then what are the models in there? I think it's Sursig 0. Yep, Sursig 0. And let's say that it's the Q value. So you can do this in your likelihood. You can now turn it into, let's see, log prior, negative 0.5. And let's say it's going to be this, yeah, minus zero point 0.5 squared. So now we have some prior that our axis ratio is close to zero point 0.5. And so this is how we implement that prior. And then if we return the sum of those two, now it's not my likelihood anymore. This is my posterior. And we're doing Bayesian analysis, just like that. And of course, you'd probably be doing something a little more complicated than that, but this is the basic idea of how you might create a soft constraint on a parameter where you're suggesting that it go to a certain value, but you're not absolutely enforcing it. And that's essentially what a prior is. It's a soft constraint in some sense, if you're thinking about it that way. Okay, so that covers all of the stuff that I wanted to talk about in this video. You now know about a few different fitters that are available, just wrapped up for you in AstroPhot, and roughly what situations you'd want to use those fitters in. Thanks to the other tutorials, you know how to create fairly detailed models of an image. And so you should be ready to do some pretty detailed fitting and actually get to those maximum likelihood points for a lot of different image types at this point. In future videos, we'll extend the different scenarios that you can run these fitting algorithms in to more complicated situations. But these fitting algorithms are probably what you're going to need for almost all situations. With that, I think we'll call that the end of the video, and I hope to see you at the next one. Definitely contact me if you have any questions. Bye-bye for now.